work on the solution. Our next topic, B.2, estimate the cost. Here, the cost, time cost. Okay, yeah. Response time cost. So the cost in time, not in money. Yeah, in time. We know time also important. Yeah. Response time. Yeah. So it's a very important resource. Yeah. Yeah. So here we like to estimate the cost. Yeah. All right. Subproblem number 1. Count the number of additions. Yeah. We need to count number of additions, number of multiplications. Let us count the number of additions first. Yeah. All right. So given a polynomial with degree n here, the highest degree term n. Yeah. If n is given, how many additions do we need to do? Can you get that answer quickly? And put your answer in the chat area to show me. So degree n. Good. Lobaba, yeah. N, good. Any other answer? Do you all agree with that N answer? Any other different answer you like to, compare with? Yeah. Is there any? Yeah, good. Anyone think of n plus 1? Any of you think of that n plus 1 as a possible? Yeah, good, Sarah. Yeah, n plus 1, yeah, because these two are most likely answers. Here, we need to compare which one is the correct one. Yeah, only one of the two must be is correct. Yeah, because the reason people can select n plus 1 because there are n plus 1 terms, right? Yeah, n plus 1 terms. The first term, the constant term, a sub 0. The last term, a sub n times x to the nth. So there are n plus 1 terms. All right, yeah. But the number of additions may not be the same as the number of terms, right? Yeah. Think about that. All right, yeah. Here, but it is very easy to get confusion. Yeah, very easy to get confusion. Yeah. So I think there is a pretty high percentage of our students may, get n plus 1. The correct answer is n, not n plus 1. Yeah. So here I like to introduce a counting method to show you how to get a correct answer without any confusion. Okay. All right. So here I like to introduce, yeah. So here, this is the answer. All right. N. Yeah. But the counting technique I like to introduce here, a very simple counting technique here. Yeah. So it's called counting by reference. Yeah. All right. Because here, if I ask you to count the number of additions directly, it may not be easy because many terms we use the representation ... right? What do you mean ... We know we skip many terms in the middle. Yeah. But the problem is these dots make us hard to keep track of the number of terms. Okay, we get lost when we see ... right? Yeah. So in order to keep track of the number of terms, then we need to find some good reference numbers, good reference. Okay, yeah. The reference will be used to keep track of the number of objects we are do the counting on. Okay, here we want to count the number of addition. All right. All right, so let me show you this method, counting by reference. Each addition corresponds to that plus sign, right? One plus sign corresponds to one addition. So if you need to count the number of additions, you just count the number of plus signs, right? Yes. But the plus sign, how to keep track of the plus sign? Yeah, here the question. Question. How to keep track of the plus sign? Okay, yeah, we get lost. Okay, 1, 2, 3, we get lost. All right, yeah. Now we need to find suitable reference to help us keep track of those plus signs. Okay, those plus signs. All right, yeah. The first plus sign we associate with the subscript 1, A sub 1, the subscript. The second plus sign we associate with the second subscript 2, and so on. All right. The last plus sign we associate with the last subscript n. Okay. Now we get a list of subscripts. That is 1, 2, 3, ... Yeah, the last one n. Okay. Yeah. Here, although we have ... here, but we know these are the natural numbers, consecutive integers, start from 1 and end with n. We won't get lost, right? When we count the number of integers in this list, we won't get lost, right? We know the answer is n. Okay. So it's very easy to keep track of these subscripts instead of those plus signs. Okay, so this method we call counting by reference. Yeah, so here let me do the summary. The essence of this method. Yeah. In this class, we will use this method many, many times. Yeah. The essence of this method: discover one-to-one correspondence between two mathematical objects. Here, one is plus sign. Yeah. Object 1, that plus sign. Object 2, a subscript. So we get a one-to-one correspondence. Right? Yeah. Yeah, quite neat. Yeah. So there, when we do the counting, yeah. Object 1, object 2, one-to-one correspondence. Yeah. Object 1 is hard to count. Yeah. It's hard to keep track of all those objects, like the plus sign, right? Hard to keep track of. Yeah, here, 1-to-1. All right. But object 2, easy to count. Yeah, easier, yeah, to count, because not hard to keep track of all these objects. There, instead of counting number of object 1 directly, we just count the number of object 2 directly. After we get the answer, we know the number of object 1 should have the same answer because 1-to-1 correspondence. That's the way we find the correct answer. Okay, this method is called counting by reference. Later, when we do other counting on other mathematical objects, yeah, if you feel hard to keep track of those objects, you can try this simple method. Okay, yeah. All right, yeah. Next, subproblem number 2. Count the number of multiplications. Now we need to get back to our previous question to count the number of multiplications for this typical term. How many? What is that number, multiplication number? Okay, yeah. Can you see it quickly? Hey, yeah. If not, yeah. So if not, yeah, let me introduce another simple way to find the answer quickly. All right, yeah. The strategy, try simpler examples. Yeah. Sometimes when we work on a particular problem and we do not feel very easy, yeah, there is one simple strategy that is very effective. Here we can try that. Yeah. All right. A1 x to the first. How many multiplications do we need in this term? A1 times x value. 1. Yes, good. All right. Let's try another one. A2 times x squared. How many multiplications do we need? All right. Yeah. Oh, x squared. Do you need a multiplication to get x squared? Yeah, 2, right? So the answer is 2. All right. Let's try another one. A3 times x cubed. How many multiplications do we need? Okay. X cubed. Yeah, 3. Good. Now, is it enough to get answer for AK times x to the kth power? K. Good. Yeah. That is the strategy. Try simple examples. After you find the answers of those simple examples, then you can quickly get the answer for the general expression. This strategy is very effective, and in this class, we will use many, many times. All right? Yeah, good. Yeah. Now, the answer is K. Yeah. All right. The last thing we need to do in order to calculate the number of time units, we need to find the total number of time units. All right, yeah. So here, let's count the number of multiplication in this small chart. Yeah. The first, the A1 x term, 1 multiplication. Yeah. So we put in the second row. Yeah. The total, we need to add all these numbers up by some formula. The formula, we're familiar with this formula, right? Yeah, in our discrete math, we learned this formula. Yeah. So the total number of multiplications here, what we get is this many multiplications. Okay, not time unit. This number is the number of multiplications, not the number of time units. All right. Yeah. Okay. Yeah. All right. The total units of time, then we get n units from additions, right? N units from additions. All right. So this number of multiplication, we need to multiply 10 units, right? Because we know each multiplication takes 10 units of time based on our assumption. Okay, so that's our assumption. All right, yeah. Yeah, 10 times 1/2, that's 5. So here we use that 5n times n plus 1. Yeah. After some simplification, we get this final answer number 5n squared plus 6n, number of time units. Okay, that's our efficiency measure or performance measure. Is it good or not? We don't know. We don't know if it's good or not. But our first step, we get that measure first. All right, yeah, all right. Next question, how to reduce this number? Yeah, we want to try if there is a, smart solution there, we can significantly reduce this number. Okay, yeah, all right. Yeah, the current solution, 5n squared plus 6n time units. Yeah. Can we reduce this number? Yeah. Not easy. Yeah. So improvement strategy. Here you can see we may need many different strategies when we solve one problem. In different steps, we may need to apply different strategies. Yeah. Here, yeah. To get another strategy, let's do some observation. Look at our, look at the answer here, all right? The total time units from two different operations, multiplications and additions. The contribution different, right? The contribution from addition, just the n, but the contribution from multiplication, 5n squared plus 5n, right? The contributions. So different. Yeah. Multiplications contributes most of it. Addition operation contributes very little. All right? Yeah. That's the property. Okay. From our observation, we find this property. That is the property. Okay. Yeah. All right. The reason is because the cost ratio, 10-to-1 ratio. Yeah. That's one factor. Cost ratio is one factor, 10-to-1, right? Another factor regarding the number of operations, one with a square polynomial, another with the linear polynomial, also quite different. Okay, two factors here. Okay. That caused a big difference in contributions. Yeah. All right. Conclusion. Now, after this observation, we want to make a conclusion. Now, in order to reduce the efficiency number significantly, where should we put our effort? Yeah. Because we have limited amount of resource and energy. Right? Yeah. So when we want to put our resource, energy, and effort, we should focus on some particular component, right? Yeah. Here, our conclusion is we focus more on multiplications, not additions, right? Addition, that number already very small, right? No room for improvement. If we focus more on multiplications, we will have more room for improvement. Right? Yeah. That will help us get to the goal, reduce the efficiency number significantly. All right? Yeah. Okay, yeah. So that's the conclusion. And this conclusion is the improvement strategy we like to take in our next step to find a better solution. Okay, all right, yeah. The strategy, reduce the number of multiplications. Okay, yeah. How? Yeah. Although we here at this point we agree This is a good strategy, right? But the question, how to do it? Okay, yeah. That's the execution step, right? Execution part is still not easy. Okay. Very hard still. Yeah. Okay.